Hi, everyone. Thank you all for coming today. So what's the big picture of this talk? Well, DP is well studied in local and central models, but today we're going to focus on the newer shuffle model. In this model, like earlier protocols for histograms demanded many messages from users. Our work reduces that cost, and we discover a neat side effect of that reduction. So to set up this talk, I'll define some terms. Users are going to be human beings, so some raw personal data that we want to keep private. And an analyzer is something or someone who wants statistics which concern the population. And we'll consider an adversary who wants data on an individual level. All right, so given this terminology, let's define differential privacy. Well, loosely speaking, it ensures that an adversary's view is insensitive to any one user. So we'll consider two data sets to be neighboring if they differ on one user's data. And a protocol is going to be differentially private if for all like neighboring inputs and for all outcomes. The likelihood of that outcome changes only slightly when we change inputs. All right, so the slight change is quantified by epsilon and delta, which is a hybrid multiplicative and additive bound. But the question we have to ask is like, how is this protocol structured, and who generates that view that we're going to be looking at? Right, so in our work, we studied the shuffle model. It has its roots in Batao et al. And was formally defined in my work. Well, we modeled the analyzer as being untrustworthy. The adversary could control it, which means users perform local randomization to protect their data. But unlike the local model, which you saw previously, there's also a service or functionality called the shuffler. It takes in the end user messages and applies a random permutation to them. Right, so it's like you're dropping off envelopes in the mailbox and it's processed in a random order. Well, the important thing is that we designed the randomizer such that this big box is privacy preserving, n executions of the randomizer followed by a shuffle. Unlike local privacy, we don't care how private R is on its own. We only care about the composition of shuffling and private randomization. Notice that we're allowing multiple messages from each user, so everybody drops off multiple envelopes in their mailbox. Right. Of course, we like to keep the volume down because that's like communication cost. So that's like one thing we want to measure. Of course, like why should we study this model of all possible models? Well, there's existing literature on shuffling, ranging from mixed nets and anonymous communication more generally. And of course, anonymity is inherently appealing to users. Like if you want to sell something or a product to your user base, anonymity is a nice thing to have. And a final, more theoretically interesting property is that shuffling bits is like the same as adding bits or counting. This is very neat because it implies easy deployment of some centrally private algorithms. Okay, so I've defined a shuffle model, but what's the problem I'm going to solve? It's called histograms. And in this problem, each user has some discrete value. And the goal is to privately estimate the counts of each domain element. So every j in the set 1 through d. And so we'll try to minimize L infinity norm, which is the maximum error of any bin. All right, so the question we'll explore is, can we get low error private histograms in this new model? And can we do so using a few messages per user? And just to clarify, by low error, I mean like polynomial in 1 over this privacy parameter and like log terms. All right, so the answer is yes. We demand only 2 messages per user when n is sufficiently large. And a side effect is that the estimates are robust to malicious users who want to bias the computation. All right, so that's the answer to our question. But just to put things in context, let's compare our work with some prior work. In prior work with Victor Balser, I have a protocol for with D messages per user, which is very large because that's the number of bins. This was improved by work by Ghazi et al. Down to polylog D, but then roughly the same team got a result that was vanishing with n. So as you increase the number of users, the number of messages per user actually goes down. But there is like a linear in D term, which is not that good. And in our work, we get best of both. We have a polylogarithmic dependence on D and like a vanishing of n property. Right, so for the rest of the talk, I'll explore like what this protocol exactly is, the experiments, and a robustness property that the protocol has. So without further ado, let's look at the protocol. So in our protocol, like each user will do the following. They'll encode their value as a one-hot string. The position of 1 is their value. Then they flip each bit with a small probability. So in the local privacy literature, that's called randomized response. And the next step is to construct extra strings of all zeros, and then repeat the bit flipping procedure. Right, so in other words, like each user makes k fake users who each have a 0 string, and then we just apply the randomized response to all strings. Right, and when we're sending all of these strings to the shuffler, who then sends it on to the analyzer, who then computes some estimate based on this set of strings. Right, so it's a somewhat straightforward protocol, but like, how do we choose parameters for privacy? Like, why is it private? Well, without loss of generality, let's look at like 2 neighboring inputs. Well, in one input, I have a 1, in the other input, I have a 2, and everybody else is the same in both data sets. And so that notice that if we give x to the protocol, the first user encodes 1 as a one-hot string, 1 followed by zeros. In the neighboring data set, we have a 0, 1 followed by zeros. So like we change one user, they change their encoding. And like fake users, in either case, they'll encode a 0 as like a string of all zeros, right? But these strings are not sent to the shuffler. They get randomized first. So like what happens? Well, the 1 gets mapped to Bernoulli 1 minus q, and zeros get mapped to Bernoulli q. So this is what the first user sends. It's a 1 long string that's randomized. And then in the other case, user 1 sends a different randomization. We just shift the bias position. And in both cases, the fake user sends a message from the product distribution, Bernoulli q. Right, so these are messages sent by each user. Now notice that like the suffix of each message is like basically the same distribution. They contain no information about the user data, so it's safe to ignore the suffix. Right? The coins do not depend on user data, so we ignore them. But also notice that on the first input, the mode of the message is 1, 0. And on the other input, the mode is 0, 1. And we focus on the mode because that ends up being the hard case for differential privacy. Right, so given this, like, how does our privacy analysis work? Well, we start off the observation that the shuffler's output is determined by counts. So it's an unordered collection of messages. So all we really have are a histogram of the frequency of messages. And so we can represent this as like a bar chart or a histogram. And again, like I note that we have 2 different inputs, neighboring, and the hard case is where we have the modes. Each user reports the mode. And this is 0, 1, 0 on input x and 0, 1 on input x prime. We also have fake users contributing messages, so we'll draw them as purple bars. And these are random values. And the second observation we have is that, well, the odds that a fake user reports 0, 1 is the same as the odds that they report 1, 0. Right? So it's a 50-50 or a fair coin, which bar they end up being in. So when there are m fake users reporting one of these 2 values, the count of 0, 1 is going to be a binomial, m comma 1/2, right? So because you have m people flipping a fair coin, this is what the frequency ends up being. All right, so we have this binomial distribution. So why is this interesting? Well, it's interesting because of the following reason. Adding this noise to a count ensures differential privacy. Well, whenever this m parameter is large relative to privacy parameters. All right, so all we have to do is ensure that m is large. And in our protocol, recall that m is the number of fake users who send either 0, 1 or 1, 0. This happens with a known probability for each fake user. We can just look at the distribution that we created earlier. And by linearity, the expectation is going to be this somewhat simple expression. But the point is that this random variable is concentrated around the expectation. So when the number of users is large, the number of fake users per real user can be any positive value. And then we'll set Q to be this appropriate value, which ends up being like 1 over nk. So 1 over number of real users times number of fake users per real user. All right, so that's the settings for differential privacy, but like, how do we actually compute with this set of strings? Well, remember that the shuffler sends a bag of strings to the analyzer, so we can compute an unbiased estimator from all these strings. I won't go into details, but suffice to say, it's a linear function of t sub j, where its number of shuffled strings with a 1 at index j. And the standard deviation of this estimator is going to be this function of q, epsilon, and delta. The smaller the privacy parameters, the more error you get. But on the other hand, small q leads to less error. And note that this error bound is for 1 bin. To cap the maximum error, we perform a union bound over d, so we get a log d term. And now remember that q was set to be something vanishing with 1 over nk. And if you plug it back into this expression, it's nk over this function. But the upshot is that if I increase the number of fake users, k, we reduce the scale of error. So this factor approaches 1 from above. Right, so this is an interesting property which bears out in the experiments. So what exactly are experiments? Well, to start off, we downloaded a list of English words, and then a set of tweets from prior work, sampling 1 word per tweet. And then we ran this fake user protocol with varying choices of k, and for this fixed set of privacy parameters. And then we also simulated an earlier protocol with the same epsilon and delta. And as we expected, increasing the count of fake users reduces the error up to a point because it starts to approach 1 from above. And so it levels off at around 4, but the change is still noticeable. And we also compared 2 protocols. The prior work has worse error in our experiments. It's an order of magnitude worse. This comes from the fact that the prior work was designed for large d, but in our case, like, the dimensionality was smaller than 1 over delta. So our protocol does better in our experiments. Let's close off with a robustness property. So what is robustness? Well, we're imagining a user who is malicious. They can send arbitrary messages to the shuffler, which will affect the computation performed by the analyzer, obviously. So as a baseline example, you can run the randomizer on value 1, which means there's going to be some bias towards 1, when maybe there shouldn't be. But there are potentially other ways of biasing the computation. So what's the worst that can happen? Well, it turns out our protocol is robust to anything a malicious user can do. And this comes from the fact that we have an estimator that's a linear function of this count, t sub j, where it's the number of messages that have a 1 in position j. And the point is that each message shifts this count by 1, right? It's a count. And any user sends a bounded number of messages, k plus 1 messages. So what this means is that a corrupt user's influence is bounded by k plus 1 times this scaling factor. And so this influence is a constant whenever k is small. Right? So as long as k is small, we have a bounded influence per user. And so we also know that other protocols have this similar linear dependence on number of messages. And so as they have more messages, they have like a worse, they're less robust to malicious users. Now, whether or not this is inherent is an interesting open question. And with that, I'll conclude my talk.
we have quite a bit of time for questions. So please, if you have any questions, step up to the podium.
So hi, Albert. I wonder what's the size of those messages?
Sorry, what's that?
What's the size of those messages?
Right. So the naive thing I drew is like the size is the length of the number of bins.
Okay.
So it's, if you have d bins, you have d bit string.
Okay.
But in principle, you can compress it because like the flipping rate is small. So the number of ones is small. So you can like just send the positions where you have one.
Okay.
That's
How does that compare to the naive scheme if you compress it? What will be the, for example, the theoretical performance of the?
Right. So it will be, so if the length naive scheme is d, the compressed scheme will be like d over n times like privacy, some function of privacy parameters.
Oh, I see.
So as you increase the number of users, like you can like shrink it more.
Okay. Thank you.
Great. I have one question. So can you say a little bit about what happens when k is large? So I think you showed that robustness holds for constant k. So what are the main challenges for extending beyond constant k?
Right. So when k is large, like any user has more influence, so like you'll be less robust. But on the other hand, like the error in the non-corrupted case will be less too, because like we also have this property where you have more fake users reduces the scaling factor that we have. Mm-hmm. So.
Okay. Are there other questions? If not, then let's thank the speaker again.